Well, hello everyone and welcome to another video. Actually, because I've been learning, I have exams in 2 weeks, and I thought I'd take a little break from learning to talk about something else. And this something else today is a stream that was done by Flatset, apparently only a few days ago from when I'm recording this. 1 day ago, as a matter of fact. And since we had a very brief chat in the comment section of my last video, thank you very much for watching, by the way. I thought I'd give it a good old go because he has 27 questions for globe the globe defenders can't answer, which is a quite inviting video topic, I'd argue. Although this video it was taken from a live stream, so I understand, of course, that it is longer. But it is an hour and 50 long, which, that's so much time. But why not start?
The Globers are former Jeopardy contestants. They won't answer any of the 27 questions.
I will certainly try my best. I can't assure you that I'm going to answer them correctly, because I will, as usually, I'll be doing those blind.
I don't
Right?
think so. Okay, so I
As
think
is
what we're going to do is with the
customary.
27 questions, we'll go through one by one and we'll maybe explain it to them. How's that sound?
Yeah.
Because, like I said, a lot of them aren't going to understand what the hell's going on. So, how the latitude lines work. It's simply just showing the apparent angular measurement away from Polaris, and that's how.
I mean, okay. When you have a sphere, right? And I'm not presupposing, because that might be something that you will say that I do, but just in general, all right, completely outside of Earth and stuff. When you have a sphere, any sphere, you want to describe points on top of that sphere, you have a couple of choices, right? You could use polar coordinates, or like spherical coordinates rather. Polar coordinates would be the equivalent in 2 dimensions. You can use spherical coordinates. Those are comprised of 2 angles and a radius. So you could say that from the center of the sphere, I have the first angle, which you need to define whether it's horizontal or vertical, right? But I go down or up, or wherever your 0 is, 63 degrees, and I go down and I go right by 8 degrees, and at a radius of 2 meters, there's the point that I would like to describe, right? That's a perfectly fine thing. You do that in physics and in mathematics a lot, that you use spherical coordinates. We also do in astronomy, of course. But the thing is that this is not exactly practical for the surface of a planet, right? Because, well, the radius is pretty much the same all the time, and even though there are, of course, variations in radius, you are hardly ever going to have a situation where you have 2 of the angle values describing the same two coming into conflict with 2 locations. This is possible if you have caves or something like that, or underground buildings, because if you only use for example, if you want to point to a building, you can use latitude and longitude, which are those 2 angles, right? They just defined them somehow. We use the equator is 90 degrees. Sure, that's fine. And the 0 meridian goes through Greenwich in London, I believe. Greenwich in England, not London. Jesus, I'm sorry. Goes for Greenwich, as far as I'm aware. And so that's just where we define it, right? But you could define them any other way. You don't have to necessarily do 90 degrees. You can use any other. It's a definition, but that's the definition that they came up with. And if you want to describe a building, you can do that, but you can't describe the floor of the building using spherical, like you're using the latitude longitude system for obvious reasons, because you can't specify a height. Obviously, with building, it's easy. You just say this and that latitude and longitude and the 3rd floor or something, right? That's easy. But you don't have to specify locations with latitude and longitude in a sphere. You can do it differently. You could do it like you pick a city, for example, and you take an angle from the city. Let's say that north is 0 degrees, and you make a full circle around that, and the distance, right? So you can say that from London, let's pick London, because for historical reasons, if we decided to do it like that, that would probably be the city that would be used. You could say London is then with it from London to I don't know, let's say Moscow, you specify an angle where north is 0 and you go clockwise, if you will, to 360, then you can point to Moscow and then you specify the distance. This would also be a completely fine way of describing all the points on the surface of a sphere. However, with this system you would have run into a bit of a problem because technically you can overshoot, right? You can say millions of kilometers and it will still be a point, which would not be all too practical. But you can through conventions get rid of those problems, right? So latitude lines, from a purely mathematical perspective, are derived just as a kind of neat idea to describe the surface of a sphere, right? Now you say that they are something to do with
Simply just showing the apparent angular measurement away from Polaris, and that's
I mean, that is a possibility, right? But I don't think that this is how it was done, to be frank. While I am certain that the measurements to the stars have contributed to that, I don't think it's solely Polaris. It will have been a whole bunch of stars, because if you only take one star, your alignment is not going to be perfect, right? Because your measurement apparatus isn't perfect. When we in astronomy, when we try to really to calibrate our telescopes before we do an observation, we use 3 stars normally, like with small telescopes, but with the big telescopes they can use, I've read in papers, up to 7 calibration stars, which makes your pointing, this is where you point, and the error of where you point, the error extremely little, right? And that's what you want to do, obviously, for measurements, obviously, right? I mean, that makes sense. So latitude lines, I would say, are first and foremost the mathematical concept behind it. Now, from a practical point of reason, you can from a practical point of view, kind of, you can say that I would argue that they are derived from, well, astronomical observations, not only from Polaris, but from many kind of views. I mean, you're only talking about latitude lines there. 1 star observations would likely be sufficient, or at least more sufficient. But I would also argue that the geophysical measurements would certainly be taken into account. For example, the from the equator and things like that, like the bulge at the equator would have to be taken into account, and all of these things, right? But I am, like, as a rough estimate, you can only, of course, use elevation measurements.
how they get 10 degrees, 20 degrees, 30 degrees, and
also, no, I mean, they don't require a 90-degree flat baseline, because even though flat earthers tend to disagree with that, you can absolutely measure angles to curved lines as per analysis and like calculus, right? You can absolutely do that. You can measure the angle to a curved line through its derivative. That's pretty standard, you know.
so forth. They don't understand that it's taken from an elevation angle that requires a 90-degree horizontal baseline.
But it doesn't
It's
require
a complete triangle.
flat baseline, right? I mean, when you measure it, you're looking straight ahead, right? I believe that's what you're attesting to, this whole sextant thing. But if you look at the horizon, that you're measuring between 2 points, right? And the points can be on any surface that you kind of want them to be. So no, it doesn't need to be flat. It's you just measure the angle between 2 points, which is, I mean, you're the 3rd point, right?
Dave,
so,
triangles McKeegan.
Triangles.
No need
Space Miner, -1. So yeah. So, do we have any Globers in the house that want to come and answer this?
I will skip a few parts between, because I'm
questions, so I can make a video about it.
Solely interested in the questions themselves.
Go on to question 2, probably.
About the things around it. Yes.
Simon Dunn will answer all your questions. Give me.
Give me.
Simon Dunn's a bigger dummy than you, Hillary.
Simon Dunn, you know what I mean?
Come on.
Hey, Friday One, thank you for coming.
Hillary, seeing as you're punting him, why don't you go fetch him?
Yeah.
Let's see if we can answer him.
Yeah, it's a good idea, Michael.
Funny thing is, I don't see Hillary.
You know, I should really start pre-checking the videos before I start recording, but I have a bit too little time for that. To be real with you, there it is.
Egan debunked the globe on the sphere on. Ooh, okay. Why, when demonstrated in real life, the shadows on the sphere are not what we observe when we look at the real moon?
Huh? What do you mean? Why, when demonstrated in real life, the shadows on a sphere are not... I will need clarification for that
This is
question.
very simple, guys.
Because the shadows on the moon are pretty much what we think they would be, and they also get rid of the notion that the moon is its own source of light, because sources of light tend not to have shadows, you know.
Guys,
But
we actually had
whole
a
different thing.
Globadoo demonstration where he took 2 spheres, and he
Okay.
places the one in front of the lights to have a shadow on the moon. And while
I mean, if you do that sort of things, you would need to of course get at least approximately get it correctly, that the light source will need to be very far away, and all of the light rays would have to come in at least approximately parallel to get at least a close to real shadow, right? Because that's if you want to test the I'm going to call it globe model, because that's the vocabulary that makes me understood the most easily. If you do that, you will need to, if you want to test it, you will need a light source that gives off parallel light, or at least nearly parallel light, and you would need to put it far enough away so that the angle doesn't, you know, cause problems. Because if I have a very extended light source, for example, like a neon light tube, I don't know what they're called in English. You know, those office lighting things that are tubes filled with neon gas or some other gas. If you have one of those and you put a ping pong ball, if you will, as your moon, well, obviously it's going to be lit more than the actual moon, because you got the angles and the geometry, the underlying geometry is all wrong, of course.
the moon shadow did not, on the demonstration, did not show the same as what we see in actual observation of the real moon.
Could you be more specific about what you mean by not the same?
So why is that?
by
Why, when they do
how
actual
much?
demonstrations, it doesn't?
Because if you take a ping pong ball, or like any other ball that is sufficiently spherical enough and not deformed, and some days, you know, you can see the moon out, and you take this ball and you hold it right in front of the moon from your vantage point, right between your eyes and the moon, it will throw the same, or like extremely close to the same shadow as on the moon. So
Port reality.
I've done it myself. That's you know how that works.
Hey Neil, got a hot mic, mate.
Sorry, could you ask the question again? Neil's here.
Yeah. I says, so why, when demonstrated in real life, the shadows on a sphere...
I disagree. I would like to see that demonstration, to be real with you, because I believe I've seen quite a few demonstrations that do line up nicely.
Shadows, we're going to need a flat baseline to measure a shadow.
Exactly.
You don't.
Exactly.
Can you if you measure a shadow, first of all, Earth's so fucking big. I'm sorry for swearing. Earth is so absolutely huge that the local terrain to up to a few hundred meters will easily outweigh any kind of curvature. At least where I live, there are a lot of hills where I live. So that's like the first point. So you obviously don't need that to measure a shadow. And if you measure the shadow on a spherical object, then it should not be straight, then should it?
We also need a positive claim about what the moon actually is.
Also true.
As well.
But this question is specifically for the people.
The moon is I'd call it a planetary body that carries the somewhat arbitrary astronomical distinction of a moon that orbits Earth and is made from, at least on the surface, mostly regolith. Yeah, it's you can call it a rock that is spherical that orbits Earth. Or no, I mean, not perfectly spherical, of course. You can see craters and stuff, but yeah, you know.
They say why? I mean, they say that it's a shadow. First of all, that's also just a claim. How do you know it's a shadow?
Because you can see the shadow in the craters. I've literally, with my tiny little, very bad telescope, like not the telescope from the university, but like the one that I own, that I bought on a garage sale for like 25 euros. And by literally holding my phone up to the ocular, I have taken a picture of the moon, where you can very, very clearly see shadows in the craters, which is not possible if it's a light source.
How do you know it's a physical object? And how do you know it's the Earth causing the shadow on the moon? Now,
It's, oh my dear, bugger me with a fish fork. The Earth is not causing a shadow on the moon. The moon throws its own shadow. It's a sphere. If you light it from one side, parts of it will have shadow on it, right? You do understand it. I have heard that claim by flat earthers a bunch of times, that we say that the Earth casts a shadow on the moon, which it only does if, like, there's a what's the word? You know, if the Earth's right in between the moon and the sun in a line. English sometimes isn't easy if you get taught things in German, or at least some of the things in German. Not important, you know. That's the only situations when they are nicely in a line where the Earth actually does throw a shadow on the moon. But all of the other times, the moon throws its own shadow.
now the funny thing is, when we take a look at demonstrations that globers do when trying to demonstrate a shadow based from a sphere onto a sphere, those shadows do not match the shadows apparent what we see on the moon.
But they usually
So
do.
I wanted
I'm asking, I mean, do it yourself, right? You can walk outside with a ball, and you will see that the shadow, if the moon's out, of course, which unfortunately it isn't. So I mean, otherwise I would do it myself today. But also we have a whole bunch of clouds, so I don't think that would work nicely. But there are a whole bunch of videos where you can show that you take a ping pong ball, or like a football or a basketball, anything that's round enough, right, and not kind of, if you do it on a balloon, of course, because a balloon is not a nice sphere, it'll not work nicely. But other than that, if you put it right between your eyes and the moon, like you kind of put it over the moon, if you will, the shadows should align very, very nicely. And in pretty much every case it does, except for when the moon is extremely low. Then you will have problems with the atmosphere, because when the moon's very low, the light of it travels through a lot of atmosphere, and that distorts the light somewhat. And then, but then the moon is going to be looking a bit straight, like jagged anyway. So, you know.
to know why is that, because if they're claiming it's because it's a sphere, that's why we see the shadow as we do.
Yes.
And this is all assuming it's shadows, by the way. Why does it look different?
No one's assuming shadows. You can see the shadows through a very cheap telescope. You can even see them with binoculars, I believe.
Because they automatically think, because of ignorance, oh, because it's sphere, it's round, it's going to show a round shape, a round sphere. Shadow. No, it doesn't. Actually,
Not necessarily.
You get the same.
That depends on where the sun is.
Shape as well, and
I mean, how? I understand how you can get some of the shadow shapes on a if the moon was a sphere, right? But first of all, that the moon does something that you call libration with an L, not vibration, but libration. So we can actually, if one observed it closely, you can actually see about 57% of the moon during a year or something like that. I'm not entirely sure on that. But so first of all, flat surfers obviously can't do that. Second thing, how would a flat shape throw a shadow that, like when you have a sickle-shaped moon? They are called that in German. Like the literal transition would be sickle-shaped, which, now that I think of it, I don't think it doesn't make much sense. You know, crescent moon. Yes, I believe that's the word I'm looking for. Now I'm very aware that you won't accept Wikipedia as proof of anything, because That's how flat surfaces roll, which, by the way, here you can nicely see the libration. But I'm talking about these kinds of shadows, right? How could a flat surface throw these kinds of shadows that are clearly done by if you look at that, and that actually looks extremely similar to one of the pictures I took. I can, if future Olaf remembers it in the editing, he will put the picture here. Very confident that he will forget about that. But from these kinds of pictures, and you can even see here, you can see that there's a shadow in the crater. There's a shadow in the crater. How can this be its own source of light, and how can you say that it doesn't throw shadows? That, to me, I'm sorry, Flatside, but that is just ridiculous to me. I do apologize, but that's how it seems to me. And with that, I'm already at 21 minutes, which is the new length kind of that my videos take. So with that, I thank you very, very much for watching, and I will look through the other questions, of course. With that, I thank you very much for watching. If you enjoyed this video, do consider leaving a like, and if I dare suggest you would subscribe, I would sincerely appreciate it. And with that, I will see you in the next part. And Flatside, but by the way, Flatside, if you're watching this, I hope you do know that this is all in good sports. You know, I'm as you know, or maybe as you have figured, I'm not that confrontative of a go chap, I'd argue, but you know, I'm doing this mostly for fun, my own fun, that is. But yeah, with that, I will see you in the next video. Have a nice time until then. Bye.